Now let's turn to our session on East Africa's potential to contribute to decarbonization at scale. The Global South is a vast, untapped source of human talent, carbon storage capacity in geological formations, and renewable energy that can help reduce atmospheric CO2 levels. And in a moment, Diana Maranga, business development leader at Octavia Carbon, will take the stage to introduce the first direct air capture company, that's a DAC company, in the Global South. Based in Nairobi, Kenya, Octavia Carbon designs, builds, and deploys DAC projects to reduce the cost of removing CO2 from the atmosphere. Diana Maranga, welcome to Wall Street Green Digital stage. Please share the Octavia Carbon story with our audience.
Yeah, of course. Thank you so much for that lovely intro, Mitch. I wonder how I can top that, but yeah. So Octavia, my name is Diana Maranga, and I'm the head of business development here at Octavia Carbon, and I work mainly in the commercialization bit, in the sale of our main product or service, however you'd want to call it, in the sale of carbon credits, which is how we keep the lights on for now. But on to Octavia and less about me. So as you mentioned, we are the Global South's first direct air capture company, and we're based in Nairobi, Kenya. And the story is quite intriguing. We were formed in 2022, in June of 2022, when Martin, who's our co-founder and CEO, he's an Austrian national, moved his life to Kenya with a strong conviction that Kenya is the best place to deploy direct air capture technology, based on the factors that you've already mentioned in renewable energy, in geological formations, in natural geological formations, and in the talent that we have in Kenya and just in the African region as well. So Octavia started in June 2022 with Martin, who's an Austrian native, and two engineers who are just straight out of uni, who, as part of their final year project, they wanted to explore direct air capture technology, but soon discovered that it was a bit hectic. It was quite a huge project take on. But even by then, they'd already interacted with Martin via the Open Air Collective. It's a lovely online forum that where they got to meet, exchange ideas, and from there they met in person and decided to start Octavia Carbon on Martin's kitchen table. Just three young, innovative, and passionate people who wanted to solve the greatest crisis of our time, which is climate change. But since then, since 2022, we are now a team of 60 with about 40 plus engineers and some in commercialization and policy as well, just actively working towards developing this niche and novel technology. But at the moment, we are currently also working on Project Hummingbird, which has an interesting backstory behind that name, which is going to be the region's first direct air capture and storage plant. And we are actively deploying machines to that plant as we speak. But why do we need carbon removal? Why do we need direct air capture technology specifically? So according to IPCC, we need to remove 5 to 10 billion tons of carbon dioxide from the atmosphere annually if we stand a chance to limit global warming below 1.5 degrees Celsius. That's an unimaginable amount. And at this point, this graph pretty much just visualizes that our current efforts as we speak only capture and remove around 2 billion tons annually. So that's a huge gap there. So this calls for innovative technology and especially engineered carbon removal solutions that will complement the existing reduction. Remember, we have to reduce emissions as much as possible, but there's always going to be a huge gap. So we need to also remove this excess CO2 from the air at a much scalable level, but also at much massive level as well. So we need to reduce what we do, but we also need to remove. So these are very complementary methods towards achieving our net zero targets. Now, this slide essentially just aims to explain at a very high level how direct air capture works. So what you see here, the two sort of renderings, is just a sort of model of our machines here at our manufacturing site. And direct air capture happens in two phases. There's the capture phase and the release phase. In the capture phase, we and at the heart of the machine is a chemical filter, which we call a sorbent, but I'll just use the word chemical filter for this presentation. It's this chemical filter that specifically isolates CO2 from the rest of atmosphere's elements. So essentially what happens in the capture phase, we blow air into the machine where it's met with this chemical filter. In Octavia's case, it just manifests itself in a white powder. So this air meets with this chemical filter inside the machine. And remember, this filter selectively isolates CO2. So the air meets the chemical filter, and then the CO2 is captured within this chemical filter, and the rest of air's elements is just blown back into the air. The oxygen, the nitrogens, etc. Once this chemical filter becomes saturated, then we begin the release phase, because this CO2 is trapped within this sort of white powder. We need to sort of agitate it, and in this case, we use low-grade heat to heat this chemical filter, which then releases the CO2. And the low-grade heat we use, and I'll jump into that a bit later, is geothermal waste heat. And then after we release this CO2, we hand it over to our storage partner, Sella Mineral Storage, who then store it in geological formations along the Rift Valley. Now, CO2 can also be, away from storage, CO2 can also be used in final clean carbon commodities, what we call the carbon to value market, where you provide this CO2 as an ingredient towards a final form. Could be graphite, could be plastic, stuff like that. So CO2 has various use cases away from obviously permanent or durable storage. So that's essentially how CO2 direct air capture works. If it's scalable and it's measurable as well. And it's often seen as the golden standard of carbon removal. So how come it's not widely adoptable? How come we're not seeing it everywhere in the world? Well, direct air capture comes with a few constraints as well. So one of the constraints that we have is that it is energy intensive. Now, the composition of CO2 in the atmosphere is, I believe, 0.04, and we want to capture metric tons of CO2. So that's a huge, huge disparity. So what happens? We need to blow massive amounts of atmospheric air in order to capture metric tons of CO2. And how do we do that? As I explained earlier, we use fans, and these fans take up a lot of energy. And this is where renewable energy comes in, because you can renewable energy, and abundant and accessible renewable energy, is crucial towards direct air capture, because as you can imagine, using what rest of the world's energy comes from the fossil fuel, perhaps, you'd be taking one step forward, which is great, which is capturing CO2, but 10 steps back if you're going to not use renewable energy. So renewable energy is key towards direct air capture. Another thing is just CO2 storage constraints, right? There's very few places in the world that can naturally and durably and permanently store CO2 for thousands and even millions of years. So there's very few places, and with CO2, you need to, CO2 transport, it's incredibly expensive, which sort of begs into the third factor, pricing. Direct air capture is quite new and novel, in the sense that it hasn't quite been explored as much as it should, as much as solar has, but it is also hardware. And hardware manufacturing is very hands-on, and this sort of can drive up labor costs as well. And with it being quite exploratory technology, it can drive the costs up quite a lot. And the fourth constraint is community acceptance. As I mentioned, it's new, it's novel. Not too many people know about it as compared to forestry projects, which are great. So people might be a bit hesitant to take on, or might shy away towards implementing and taking on new technology. But at Octavia, we solve that constraints using geothermal DAC. Now, Kenya's grid is over 90% renewable, which is absolutely amazing. And for us at Octavia, we have specifically engineered our machines to utilize 80% of our energy needs. We will need geothermal waste heat, which is abundantly and readily available. As I mentioned, Kenya's grid is 93%, over 90% renewable, and over half of that is in geothermal, and the rest is in hydro, wind, solar, etc. So we have, and this renewable energy is also in excess, but I'll jump into that a bit later. In geology, the Kenyan Rift is very rich in basaltic rock, which is essential volcanic rock. And this basaltic rock is key towards durable storage of CO2, in the sense that we get to inject, at least our storage partners get to inject this CO2 into this geological formations very, very deep underground, where it reacts with this rock to form carbonate minerals. So in a sense, it forms rock in on itself. So this owes to the durability and the permanent storage of CO2. And in talent, as Mitch mentioned earlier, we have young, innovative talent, but at the same time, and this shocks a few amount of people, Kenya's median age is 19 to 21. So we have a very young workforce, but a booming workforce as well. According to WHO, they predict that the population will double by the time we reach 2060 or 2050 thereabouts. So the population is young, it's growing, and it's young and innovative as well. And with talent, with data capture more specifically, you need to marshal brains into it, owing to its novelty, but also its manufacturing. As I mentioned earlier, it's very hands-on, it's hardware. So that is how we are also very well positioned towards deploying DAC, but also scaling it down the cost curve. And what you also have to remember, in Kenya and maybe perhaps Africa as a region, we have a very low-cost manufacturing base, meaning we can get to manufacture at a fraction of the cost as compared to our peers in the north, but we can also afford to give our talent, our employees, a very lovely lifestyle, very good life at a fraction of the cost as well. Now, in co-benefits, we have policymaker buy-in as well as community buy-in. We engage a lot with the community where we're going to deploy and just assure them of everything, but more specifically, towards Octavia, we aim to benefit the community both socially and economically by our various initiatives. We work with the local technical colleges around our deployment area. One of our apprentices is from the community area that we're in and actually works at Octavia, but also in policymaker buy-in, in the sense that we work very closely with the Kenyan government, and actually the Kenyan climate envoy, who's an advisor to the president, sits on our board of advisors. This just goes to show how much support we have from the government, but also from the community we deploy in. Now, in the 2.5-ish years, I think I can say that, we've made a lot of progress. One, in the patented chemistry and process engineering, where we've patented, that's a difficult word, patented our chemistry regionally, but also our engineering. And what you can see here is part of our patented tech as well, in the sense that, as I've mentioned earlier, we utilize low-grade heat, and low-grade heat is about 80 to 90 degrees Celsius in geothermal waste heat, but also in industrial sources. And we pride ourselves in modularity as well, in the sense that we deploy very, I'd say, relatively at smaller scale machines, DAC machines, which allows us to build fast, fail fast, and learn fast. So that's modularity allows for fast iteration processes. And if you come to our manufacturing facilities now, you'll find a very fast prototype all the way to the machines that we're currently deploying as we speak to our deployment site. So in those 2 or so years, we've been able to build 8 to 9 at scale modular DAC machines, and that's no easy feat. And another thing that obviously uniquely separates us from the rest is just innovative CO2 storage via the Kenya Rift Valley, via our storage partners, who are Stellar Mineral Storage. Now, this is just, as I mentioned earlier, just a history of all the machines we've been able to build in 2 or so years, up from the very corner there to what you see on the ground here. And this is also a lovely picture of the talented and young innovative engineers that we have at Octavia. So what you see here is what we're working towards. This is what keeps us up at night, at least most of our engineers, and this is what we're actively deploying to. So what you see here is our deployment site, and we've been able to do a lot of earthworks and civil works, just laying out the land, and we've been able to make significant progress on that. This photo was taken, I believe, a month ago. And if you go there now, if I was to upload a more recent picture, it's vastly different. We've already deployed our machines there as we speak. We're assembling them, and our engineering team is working really hard to have them operational by the end of this week. And we're deploying in phases as well, due to various reasons, but also we need to learn what they call the known unknowns and the unknown unknowns. And believe me, the testing, the commissioning tests, and the decommissioning tests have been super helpful in that. So this is just a framework or a skeleton, if I can call it that, of Project Hummingbird, which is bound to be the world's second dark and CO2 storage site, and obviously the first in the global south and first in Africa as well. So I mentioned earlier that Project Hummingbird has an interesting story behind the title, or just the name of the project itself. We got the inspiration from Professor Wangari Maathai. I hope some members of the audience recognize that name, but just as a brief history, she was the first Eastern Central African woman to win a Nobel, to first complete a doctorate, and second, to win I believe, first African woman to win a Nobel Peace Prize just for her efforts in environmental conservation. But during her tenure and her time, she unfortunately passed on. She spoke about a folklore called the Hummingbird Story. Now, in this Hummingbird story, there's a forest burning up, and several animals in the forest away. And obviously, they leave the forest and go to the borders of the forest and look at it in dismay and wonder, what do we do? What can we do here? And the hummingbird, as we all know, is a tiny bird with a tiny beak. The hummingbird was going to the river and dropping droplets of water on the fire. And obviously, all the animals, the elephants, were wondering, what are you doing? And the hummingbird told them, I'm doing what I can with what I have. So we draw a lot of inspiration from this story, simply because, as we may know, Africa has contributed the least towards the global emissions, but we are also disproportionately affected by the drastic effects of climate change. At Octavia, we are pursuing a pretty uncharted territory here in Kenya by pursuing direct air capture technology, and also just pursuing the technology in and of itself, given it's quite novel and quite new. So we draw a lot of inspiration from that hummingbird story, hence the name Project Hummingbird, with the sense that we're doing what we can with what we have. Now, we've made significant amount of progress since. Today, Octavia is the world's 5th largest direct air capture company in matters of staff capacity. And I mentioned we are about 60 staff with about over 40 engineers now. So far, we've been able to have $1.4 million worth of contracted revenue. And by contracted revenue from the capture and the storage, permanent storage of CO2, we've been able to sell carbon credits, of which 85% of that are prepaid. So we've had an impressive run of traction so far. And as I mentioned earlier, we have 2 patents, and we're filing one granted regionally, and we're looking to file one mostly in the US or in Europe. We've been able to reach an impressive 1,000 operational hours from our dark machines. And as we speak, we are actively deploying and assembling machines to the second ever pilot of a dark and storage plant in the world. So we are also market leading in quality, delivery timelines, cost benefits, etc. One notable achievement that we've been able to have is that we're, sorry?
I'm sorry, we have reached time and we have our next. I want to thank you very much for sharing the Octavia story. I'd love to ask a few questions, and perhaps we can do that off. We've been speaking with Diana Maranga. She's business development lead at Octavia Carbon. You can learn more about Octavia Carbon at octaviacarbon.com. It's all one word, no space, no dash, octaviacarbon.com. Check it out. And stay tuned for a conversation with One Planet Partners' Bobby Pauly about the role of private equity and venture capital in accelerating the Indian climate tech industry. We'll be right back.